All right, welcome back. So, having seen integrals apply to areas, having seen integrals apply to volumes, having seen integrals apply to physical work, we're now going to see an application, if you will, within sort of a mathematical setting, more puritanical, I suppose, but so be it. We're going to be talking about average value of a function on an interval and sort of the context therein. In fact, it very much relates to average in the conventional sense, and I'm going to try to draw the analogy there, and then we'll ultimately look at a few implications of how average value for a function sort of makes nice harmonious sense with what we know average to be. So let's just start with a basic example. I mean, what if we want to find the average of 2, 8, and 11? I'm sure you're familiar with this idea. Algebraically, we just take 2 plus 8 plus 11 and divide by 3 the number of numbers. And let's see, that turns out to be 21 over 3, which is just 7. And from some point of view, that offers us nothing new from what we previously have known or have seen. What I want to offer us is a new way to view average through a geometric interpretation, because this will actually help us when it comes to the calculus. So to imagine geometrically average, what I want you to do is imagine a bar graph that is associated with this data. So each bar of the graph would be sort of 1 unit wide, and the first bar of the graph would be 2 units tall, because that first data point was 2. The second bar of the graph would be 8 units tall, because that second data point was 8. And the last bar of the graph would be 11 units tall, because that last data point was 11. So here is a geometric representation of this data set 2, 8, 11. And again, think of each of these bars as being of width 1. So the total width here of all the bars is 3. Now, what we want to do is somehow find the average, 7, from this geometric picture, and in fact, we can. Note this total width is exactly what we were dividing by previously. We were dividing by 3. So when it comes to the average, in this geometric interpretation, we want to divide by total width. But the question is, what do we want to divide by total width? Well, we want to divide 21 by total width. But how are we going to get 21 from this picture? Well, geometrically, we get 21 from the picture by computing the total area of each of the bars. Check it out. What's the area of this first bar? Well, this first bar is 1 unit wide and 2 units tall. So the area here is 2. This next bar is also 1 unit wide, but it is 8 units tall. So the area here is 8. This last bar is also 1 unit wide, but now 11 units tall. So its area is 11. Just take length times width for each of those bars. But wait, if you've got area 2, area 8, and area 11, notice the total area is that 21, which was the numerator of our algebraic computation of average. So, well, with this being said, we now have a geometric interpretation for average as total area divided by total width. If I may, let's take this analogy and extend it now to a function. Well, this function has values that undulate between, well, maybe there's some maximum value up here, let's call it capital M, and some minimum value here, let's call it little m. And so, yeah, the function values are between capital M and little m. But what's the average of the function values along this interval? Well, taking a cue from our geometric interpretation of average from the conventional sense, what if we just computed total area and divided by total width? Well, what's the total width in this case? The total width is the distance between, I'll put total width here, total width is the distance between A and B, which we know, just take big one minus little one, so that's B minus A. And what's the total area? Well, hey, the total area is just the integral from a to b of f of x dx. And well, then if we wanted to compute the average, in this case, this would be the average value of our function f of x on the interval ab. What do we need to do? We need to take the integral for the total area and divide it by, oh, that pen is dying. Let me reset this. Forgive the delay. Let's see, average value of f of x on AB, the total area divided by the total width. And hey, that is a nice expression, which, hey, we could compute this, right? Because if you know the function little f, you could just integrate evaluated b, evaluated a, and then divide by b minus a. And, well, hey, that would give you the average value of the function in a similar way to average in the conventional sense. I'm going to pause the video here, scrub the slate clean, and then discuss a few implications, because this notion of average value here for a function actually harmonizes with our intuition for average in the conventional sense. Give me a moment. All right, so to pick back up with average value here, recall that we recently had computed this formula for the average value of a function. And, well, I just want to discuss a couple facts related that are ultimately implications and harmonize nicely with what we know average to be. So average value of f of x is always going to be between the minimum value and the maximum value of the function. And, well, this can be thought of because, well, what if we just take a snapshot of that picture over there on the other side of the board? So we've got this area region here like so. And what do? Now, imagine a rectangle that was as tall as the maximum was tall of our function. And then imagine we have another rectangle that was as tall as our minimum was tall. Well, there are three area regions here, one defined by that maximal rectangle, one defined by the minimum rectangle, and one defined by our function. And in fact, the area defined by the maximal rectangle is the biggest. This is going to be bigger than or equal to the area defined by the, whoops, that was excessive, the function's graph, which has more area than the minimal rectangle. But now we can compute each of the areas of these regions, right? Because this large region has an area of m times b minus a, where m is the capital M for max. This region in the middle has an area of integral from a to b of f of x dx. And this minimal rectangle has an area of little m times b minus a, right? Because the width is b minus a, the height is little m. It's no more complicated than that when you've got a rectangle. But now, what we're going to do is divide each of these areas by b minus a. So we're going to divide by b minus a each of these areas. And, well, m divided by b minus a is just m. Oops, that was an orange m. Give me a second. Divide the area by b minus a, and you get the average value. Divide the little m times b minus a by b minus a, and you get little m. But now, check it out. Within this box, you get the statement that harmonizes quite nicely with average value as you would hope it to be. The average value should be between big M and little m. In some sense, you can almost think of average value like a Goldilocks number, whereas little m is too small and big M is too large. The average value is sort of just right. So if you're imagining on this picture where the average value might be, the average value is going to be just right in terms of where it cuts into our picture. It may not be exactly between big M and little m, but it is going to be located in such a location that the area contained within that just right rectangle contains exactly as much area as is under the function. And you can show this because if you just took this expression for average value and you multiplied both sides by b minus a, on the left-hand side, you would get the area, average value times b minus a, of that average value rectangle. And on the right-hand side, you'd get the area under the curve. So in some sense, the average value is the height of a rectangle that is just right, not too small, not too large, to encompass the exact amount of area that is under our function. So kind of a cool fact, and frankly, harmonizes with our notion of average in general, right? We had that example to start with like 2, 8, and 11, and the average was 7, right? If I recall correctly from our initial example. And so, yeah, right? I mean, the average is between the minimum and the maximum. That's what you would expect average to do. And in fact, average value of a function abides by this exact same intuition. So that's nice. And it's especially nice to imagine that average value rectangle drawn in, knowing that average value rectangle is going to encompass exactly as much area contained within it as is under our functions graph. So kind of a cool idea, kind of a cool thought. Yeah, you can think of Goldilocks in some sense with this average value notion. Now, something that occurs within the functional realm that does not always occur within the standard conventional realm of average, right? I mean, if you've got 2, 8, and 11 and the average is 7, 7 does not appear amid the data. However, if you look at this picture where we've drawn in the average value, it does appear that the function attains its average value at some point. There's some point C here where the function attains its average value. And well, in fact, that is just a function of the fact that our function little f is continuous. So if you've got a continuous function, then there's some point in the domain where the function evaluates to equal its average value, which is kind of nice, right? Because in the case of just discrete data that you're computing the average of, you don't necessarily attain the average ever, right? I mean, if you complete this course and at the end of the day, your average is like 83.67 or something, it doesn't mean that you ever scored 83.67 on a single assignment. However, if you're computing the average value of a function that is continuous, because the function is continuous, it will attain every value between its max and min, right? That's the intermediate value property of a continuous function. And the intermediate value property of a continuous function, the fact that every value between the max and min is attained, will guarantee that the average value is attained along the way. So essentially, this fact is a consequence of the intermediate value property of continuous functions. You've got a continuous function. It's going to attain every value between its max and min, which means it's going to attain the average value. And once you compute the average value of a function, if you express f of c and set it equal to the average value, you could actually solve to determine exactly where that average value occurred. So if the temperature during the day went from whatever it did in the middle of the day to whatever it did in the middle of the night, and you want to know where the average temperature for the day occurred, you could find the time at which it occurred if you ultimately solved the expression like f of c equals average value. Well, in the case that it was a temperature situation, that would certainly make sense. But hey, this rounds out a nice introductory understanding to what average value is in a geometric sense, how it relates to what we knew average to be in a conventional sense, how this new notion of average value of a function harmonizes with what we expect average to be, some number between a min and a max, how there's a nice geometric interpretation even of that. You've got this Goldilocks rectangle, and then even the fact that continuous functions are sort of in some sense superior to the discrete case where the average may not necessarily be attained amid the data. If you've got a continuous function and you're attaining every value between the max and the min, hey, you're attaining the average value somewhere along the way. So not too bad. This average value thing is pretty well behaved. And hey, a nice cap off to our study of applications of integration in Chapter 6.